Okay, welcome back Physics 30s to our next lesson. This is 2.5, and today we're going to be looking at linearizing curved graphs. Okay, so in the last lesson, we looked at how you can graph a linear relationship and get valuable information from the slope and the y-intercept. So let's say I take a sphere of charge positive 1.0 microcoulombs, and I put it next to this other sphere with an unknown negative charge. And in an experiment to determine the charge of that negative sphere, I set the spheres 12 centimeters apart and then measured the electric force that is going to be pulling them together. And then to build a table of data, I vary the charge on my positive sphere and measure the corresponding force on the negative sphere. Now, since I've manipulated the charge and measured the force, I can use my equation Fe is equal to kq1q2 over r squared and manipulate this to set it up to match y is equal to mx plus b. I line it up so the y is the force, the slope, or the m is kq1 over r squared, and the q2 is going to be on the x. There's also a plus b, but since there's going to be no plus in this equation, that would just be plus 0. I then draw my graph with the force on the y-axis, the q on the x, and I should get a straight line where the slope is equal to kq over r squared. I find two intersecting points so I can get a good slope, and then I figure out the value for the slope. Now my equation to figure out that charge is slope times r squared divided by k. Since I know slope, r squared, and k, I can figure out my q or my charge, and I get a value of 2.5 microcoulombs. And that process is really useful and applies to a lot of equations since there's a lot of linear relationships. But sometimes we run into this problem. Now, there could be a similar experiment to determine the charge of this mass where instead of changing the charge, we actually change the radius. So I start with a small radius, then I make it bigger, and then I make it bigger. And again, I keep measuring the force that is going to be pulling on that gold mass. So let's say I do that and I measure my R to be in meters 0.1, 0.15, and I'm measuring the force to be 8.99, 4.0, and you can see these corresponding values. Then similar to the last one, I set up my equation Fe is equal to kq1 q2 over r squared, and I try to separate it so that I have my measured r value as x and my Fe is y, and I end up getting an equation like this, where I can see that y is equal to mx, and my slope would be kq1 q2, but I can't get r by itself completely. It still has this 1 over r squared, and I can't pull that apart without changing the y. The force is proportional to 1 over r squared. And if I graph the radius compared to the force, I get a curve like this. I can't get a straight line by going force versus r. So what do we do in this situation? Well, the solution is actually not too bad. We're going to keep most of this the same. We're still going to have Fe as our y, kq1, q2 as our m, but instead of having x as r, we're going to take that term that this is getting multiplied in that x position, the 1 over r squared, and make that our x variable. So now we're not going to be putting r values, we're going to be putting 1 over r squared values on the x-axis. So let's put this in our chart as we have 1 over r squared, and let's convert our r's to 1 over r squared. So how we're going to do that is we're going to do 1 divided by 0.1 squared to get our first value of 100, and then keep transferring the data over. So now I have this table of 1 over r squared values. And I'll put those numbers on the x and the force on the y. Now let's change the x-axis from Fe versus r to Fe versus 1 over r squared. And when I plot those values, I do get a straight line. And then based off the formula we saw before, the slope of this line is equal to kq1 q2. So then I can calculate the slope, divide by kq1, because I know both of those things, and I get the q as, again, 2.5 microcoulombs. This process is called line straightening or linearizing a curved graph. So basically what we're going to do is we're going to attempt to align it to y is equal to mx plus b, just like we did before. However, if the x variable cannot be isolated, there's some operations like squareds or inverses that we can't get rid of without affecting y or causing that not to be an isolated variable. So all we're going to do is we're going to graph the variable with those remaining operations to it. So if it's squared, we're going to graph against x squared, not just x. If it's 1 over x, we're going to graph against 1 over x, not just x. And this should remove those operations and remove the curve. So then we make a table of values with this operation being applied to that variable as we saw in that example. Just to show you another example of where this process could apply, this is an example of a lab often done in Physics 20 where we have a mass on an air table here, so it's trying to be frictionless, and then we have a mass over here that is going to be accelerated due to gravity. They're attached by a string, so they're going to move together. So when we run this experiment, the mass falls and the system moves across like this. And because this is on an air table with spark tape, we are able to measure the acceleration with dots that go along on the spark table. And then we repeat this experiment and add on different masses. So in this experiment, we're going to measure the acceleration, manipulate the mass, and what we're going to try to find information about is the force of gravity that is pulling this system down. And the formula relating these variables is F is equal to ma. And so we are going to be measuring the acceleration, changing the mass. So that means that our acceleration should be our y value and our m should be our x. So to set this up for y is equal to mx plus b, I'm going to take a is equal to f divided by m. And then again, I'm going to isolate that m or x variable, and I get a is equal to f times 1 over m. I can't get the 1 over m to be gone without affecting that acceleration. And if I were to create a graph with mass and acceleration, I would end up getting a curved graph similar to the one that we saw in the last example. So what I would do here is I would make my y variable a, I'm going to keep that the same, and I'm going to not just put m on the x-axis here, but I'm going to put 1 over m as my values on the x-axis. That will leave force to be my slope. I know there's another m representing slopes, that might be confusing, but that's just the formula for a line. This is representing mass. So y will be acceleration, 1 over m will go on my x, so I'll put 1 over m here instead, and that will result in a straight line with the slope being equal to our force, which is what we're trying to measure in this experiment. Now, before we just start plotting the points of 1 over m, it's good to make a table of value with these numbers. So we're going to make a table of values with our measured acceleration, and we have those values filled in. And then we don't just put mass. We can start by putting the mass values, but then we should also put another column of 1 over mass and convert those values to 1 over m. So for example, if this mass was 0.5 kilograms, 1 over 0.5 kilograms would be 2 for our value there. And those are the numbers they're going to be going on our x-axis to make this a straight line. So then we're going to graph this on x and this on y. Okay, so I hope that video helped you to understand line straightening and what to do when you get a curved graph. Thank you for watching this video, and I will see you in the next one.